Assalamualaikum warahmatullahi wabarakatuh. In this video presentation, we are going to present about two theorems under permutation group and finally generated abelian group. This video presentation is for subject MAT 652 Algebraic Structures.
Assalamualaikum warahmatullahi wabarakatuh. My name is Natasha Ruzain binti Mansul and my partner is Nur Hidayah binti Norani and we are from N4CS2495B3.
Next, I'm going to present about the first theorem. Let A be a non-empty set and let SE be the collection for all permutation of A, then SE is a group under permutation multiplication. So next, we gotta prove this theorem. So first condition, we have shown that composition of two permutation of A yields a permutation of A, so SE is closed under permutation multiplication. So the second condition, non-permutation multiplication is defined as a function composition, and in which function composition is associative. Hence, G1 is satisfied. So, how to know the associativity? The permutation multiplication is composition function. The composition of function is associative, therefore, the permutation multiplication is associative. So, for the next condition, the permutation iota such that iota A equal to A for all small a element of capital A acts as identity, therefore G2 is satisfied. For the last condition, for a permutation sigma, the inverse function sigma inverse is the permutation that reverses the direction of the mapping sigma, that is sigma inverse A is the element A prime of A such that A equal to sigma A prime. The existence of exactly one such element A prime is a consequence of the fact that as a function sigma is both one-to-one and onto, for each small a element of capital A, we have this, and also this, so that sigma inverse, sigma and sigma inverse are both the permutation iota, thus G3 is satisfied. Next, we will discuss about the example 1. We have example of permutation group of 3 particles as 3. So for 3 elements, number of permutation equal to 3 factorial equal to 6, which is we must have 6 permutations function. So this is the permutation function with E equal to 1, 1, 2, 2, 3, T. So this is mean that map 1, map element 1 to element 1, map element 2 to element 2, map element 3 to element 3. So this is the rest of the permutation function. So what will be possible states of the system containing 3 particles? It will have 1, 2, 3. It means the first particle at position 1, second particle at position 2, and third particle at position 3. So this is the rest of the possible state of the system. Therefore, in a 6 different way that we can choose the position of the particle. So now, let's prove it. 6 permutation is a group permutation by 4 conditions that we discussed earlier. So first property is closure property. So here we are taking binary of operation between A and C. And the binary operation is composition permutation. Okay, next we just put AC and X2. So first we will operate C and X2. So how? So first we replace the first element by the second element. So what is the second element? Is 3. So this is 3. Then the second element by the first element. So what is the first element? Is 2. So this is 2. So the third element by the third element, what is the third element? Is 1. So this is 1. So 3 to 1. So this is A and the new binary. So we put the same way the first element with by the second element. What is the second element? Is 2. So this is 2. So the rest. So we will get the answer the same as X4, 2, 1, 3. So this is 2, 1, 3. After that, we taking the binary of operation of F, X2. So this is F, this is X2. The same way like before. Then we get X4. So we can show that this is the same result, X4 equal to X4. So we can say that AC equal to 4. So this is it means that the product of between 2 element group is equal to another group, therefore it satisfies the closure property. So we continue with the second property, which is identity property. We choose AE, the binary operation of AE X2 equal to this is E, and this is X2. The operation is the same way like before. Then we get the answer is similar with x3. So this is x3. So we choose binary operation of E x2 equal to E x2. Then we get the same answer x3. Therefore, we can say that EE equal to E. So E is identity element. Therefore, it is satisfied the identity property. So for the third condition, which is inverse property, then we choose operation AB x2, which is this A, this is B, this is x2. Then the operation is the same way like before. Then we get the answer x2. Then after that, we choose E x2 as a binary operation. Then we operate, we get the same answer x2. So we can say that AB equal to E. So B is inverse of A and E is inverse of B. Therefore, it is satisfied the inverse property. So next, we go to the last condition, which is associative property. So associative property is ACB equal to ACB. So FB equal to AF is same way as AC equal to F and CB equal to F. Then D equal to D as FB equal to D and EF equal to D. Therefore, we have satisfied all four properties of the group.
For question 2, we wish to solve if M divides the order of a finite abelian group G, then G has subgroup of order M. Theorem 9.12, primary factor version of the fundamental theorem of finitely generated abelian group, state that every finitely generated abelian group G is isomorphic to a direct product of cyclic groups in the form of integer p1 to the power of r1 times integer p2 to the power of r2 times until integer pn to the power of rn and so on, where pi are primes, not necessarily distinct, and the ri are positive integers. The direct product is unique except for possible rearrangement of the factors, that is the number. Betty, number of G of factors integer is unique and the prime powers pi to the power of ri are unique. Theorem 9.19 states that if M divides the order of a finite abelian group G, then G has subgroup of order M. This is what we want to prove. So by theorem 9.12, we can think of G as being integer modulo P1 power of R1 times integer modulo P2 power of R2 times until integer modulo Pn power of Rn, where not all primes Pi need to be distinct. Since P1 power of R1 times P2 power of R2 until Pn power of Rn is the order of G, then M must be of the form P1 power of S1 times P2 power of S2 times until Pn power of Sn, where Si is in between 0 and Ri. By theorem 6.15, Pi power of Ri minus Si generates a cyclic subgroup of integer modulo Pi power of Ri of order equal to the quotient of Pi power of Ri by the GCD of Pi power of Ri and Pi power of Ri minus Si. But the GCD of Pi power of Ri and Pi power of Ri minus Si is Pi power of Ri minus Si. Thus, Pi power of Ri minus Si generates a cyclic subgroup of integer modulo Pi power of Ri of order Pi power of Ri divides with Pi power of Ri minus Si equal to Pi power of Si. Recalling that cyclic subgroup of G generated by A denotes the cyclic subgroup generated by A, we see that cyclic subgroup generated by P1 power of R1 minus S1 times cyclic subgroup of P2 power of R2 minus S2 times until cyclic subgroup Pn power of Rn minus Sn is the required subgroup of order M. Example 2.1, consider the scenario where we want to categorize all abelian group of order 540. By using the long division, the result is as follows. We get 1 as the remainder, where 1 is the divisor. Thus, there is a subgroup of order 540 where we express 540 as a product of prime powers 2 squared times 3 cubed times 5. Then, by using the fundamental theorem of finitely generated abelian groups, we get the following 6 possibilities as you can see on the screen. For example 2.2, assume that we wish to classify all abelian groups of order 360 by using the long division. The result is as follows. We get also remainder 1 where 1 is the divisor. Consequently, there is a subgroup of order 360 where we interpret 360 as a product of prime powers 2 cubed times 3 squared times 5. Next, by using the fundamental theorem of finitely generated abelian groups, the possibilities can be seen below as you can see on the screen too.
In summary, 2 theorems under the finitely abelian group and permutation group have been proven in this report. The 4 conditions of closure, associativity, identity, and inverse were demonstrated. As a result, it is a group with respect to composition of function since all 4 conditions for a group are satisfied.
A finitely generated abelian group, according to the fundamental theorem, is the direct summation of a free abelian group of finite rank and a finite abelian group, each of which is distinct up to isomorphism. The only possibility 2 finitely generated abelian groups may be isomorphic is if and only if they share the same free rank and invariant factors.
Thank you. That's all from us.